I'm just going to write down a problem that we'll look at. So what I'm going to do today is actually start with this linear program, which is a fairly small linear programming problem that can be solved fairly easily. And first we're going to look at a picture and observe what the optimal solution is. But then, as we mentioned last time, if you have a few hundred variables or a few thousand variables, there's no way you'll be able to draw a picture. The question is, in those cases, how would you translate this intuition that you get from looking at the picture to a method that does not rely on the picture itself? And we'll develop a simplex method to solve linear programs. So I'm going to do this for a little bit. Then I'm going to also show you how this method actually works and how you can carry out these computations without rewriting the system of equations as you go along. Okay? So let me actually draw the picture and make a few remarks before we continue. Okay? So this is going to be x1 and x2. So recall that we are interested in all x1, x2 pairs that satisfy all of these constraints. Okay? So to draw the first constraint, which says minus x2 minus x1 is at most 5, you can check that when x1 is 0, this just says x2 should be at most 5. Okay? So that's say this point. When x1 is 1, this says x2 should be at most 6. Okay? So you get something like this. And so you have a line that goes like this. So that's the line x2 minus x1 equal to 5. Okay? And on one side of the line, you'll have inequality this way, and the other side of the line, you'll have inequality that way. Okay? So it's easy to check that all the x1, x2 satisfying this constraint lie on this side of the line. Okay? So some general terminology, such a line this is a line in two-dimensional space. And in n dimensions, when you plot an equation like this, you get what is called a hyperplane. Okay? And a hyperplane divides the space into two parts. And therefore, this side of each side of the hyperplane is called a half space. Okay? So, in general, this is a half space, and this is a hyperplane. Okay. Now similarly, we can draw this equation, x1 is at most 20, and that looks like something like this. Okay. So again, this is another hyperplane, and this half space is the feasible portion of the hyperplane with respect to that constraint. This half space is feasible, and this half space is not, with respect to that particular inequality. And of course, there's this constraint which says x1 plus 3x2 is at most 35. So this point, is 35, 0, and as I increase x2, so when x2 is made 1, I get x1 to be at most 32. Okay? So it's something like this. So you get a line. Okay, so that is a straight line. And once again, it's easy to check that the feasible portion of the feasible region with respect to that constraint is actually on this side of the line. So, putting all of this together, the feasible region for the problem is something like this. Okay, you have this line, you have this line, so those are all x1, x2 pairs that satisfy all of these constraints. And of course, I have the non-negativity that I've implicitly assumed in all of this anyway, because we're focusing on just this quadrant. Okay? So any questions about just getting this picture? Okay. Now, once you have the picture, it's actually fairly easy to determine the various points that are of interest, right? So this is the origin. This, as I said, is the point 0, 5. This is 20, 0. And how would you determine this point? So again, x1 is 20. Sorry? 20 and 5. And the way you get it is observing that this point is the unique solution to two equations, one given by this line, which is x1 equals 20, and the other given by this line, which is x1 plus 3x2 equals 35. If you solve these two equations, you get exactly this point. Okay. And this is actually, yes, 510. So again, you can check that by plugging in those values into these two equations, because that point is the intersection of those two equations. Okay. So x2 minus x1 is 5, so it satisfies, it does lie on this line. And similarly, x1 plus 3x2 is 35, so it lies on this line. Okay. So we have all of the 5 boundary points of the feasible region. And of course, any point that's a weighted combination of these two is going to generate this line segment. If you take this and look at any weighted combination, you're going to get this line and so on. Okay? So the feasible region is what's called the convex hull of all of these points. Okay. Okay. Now, how will you sort of solve the linear program once you have this representation of the feasible region? So one way to do it is to look at what is called an isocost line. Okay. So what does that mean? So let's actually look at the line 2x1 plus 3x2 equals, let's say, 10. Okay. So what does this line look like? So of course when x1 is 5, x2 has to be 0. So you have some point like this on that line. Okay. So that's 5, 0. As you can see, my picture is not to scale. And then what about when x1 is 0, x2 is, 3 and a third? Okay. So that's, I guess, somewhere here. So you get a line like that. Okay. So this is the line z equals 10. Okay. And I'm using z to indicate the objective function. So you can now think about taking this line and moving it in a direction in which the objective value increases. Now, why do we want to do that? Well, one way to solve this problem is to keep asking questions of the following form. Can I find a pair of x1 and x1? Can I find values of x1 and x2 such that 2x1 plus 3x2 is 20? Okay. And if you can, then ask yourself whether you can find a pair of x1, x2 such that 2x1 plus 3x2 is 70. Okay. So you keep asking yourself this question by gradually increasing the right-hand side, and the largest value for which the answer is yes gives you an optimal solution. Okay. Now, the line 2x1 plus 3x2 equals 10 and the line 2x1 plus 3x2 equals 40, these two are just parallel lines, right? It's just taking this and shifting it upward because that's the direction in which the objective value increases. So rather than actually examining this continuum of values and checking whether that line intersects the feasible region, you can actually think about taking this line and pushing it upward. Okay. And the last point where it intersects this feasible region is going to be an optimal solution. Okay. So as you take this line and move it up, at some point it's going to intersect the feasible region, but any further push is going to make it not intersect the feasible region. And that will give you an optimal solution. Okay? So presumably a lot of you have seen this already, and if you haven't, you can look at the book to see how this is done precisely. So, of course, in our particular case, it's actually fairly easy to see. Of course, from my picture, it's a little difficult to see. But if you draw the right picture, it's fairly easy to see that you're going to get an optimal solution somewhere at this point. Okay, so this is going to be so this. Okay. Now, of course, this, as I said, this is not a particularly good picture, but if you're not completely convinced, even from this picture, you can sort of make the following inferences that are right. That as I move this line upward, the only 2 points that are of interest are these two. Okay, so you can just plug in the values of this point and see which is better. Okay. Okay. Now, this pictorial argument should also convince you of one thing, which is that there is always going to be a point like this that's optimal, meaning what's called a corner point. Okay? So you can easily see that a point that's somewhere in the interior, okay, such a point cannot be the only optimal solution of any problem. Okay? Now, why is that? Well, if this is an optimal solution, that means that if I take, this has a certain objective value. Okay? And if I look at a line, 2x1 plus, whatever the objective function is, z equals that value, it's going to pass through this point. But because this is in the interior, I should be able to move this line up or down. Okay? And in one of these directions, the objective value cannot go down. And therefore, this cannot be the only optimal solution. Okay? Now, I'm couching this argument very carefully. I'm not saying that this cannot be an optimal solution. Okay? This could be an optimal solution. So, for instance, if your objective function is maximize 0x1 plus 0x2, then this is an optimal solution. And so is every other point. Okay? So what I'm trying to say is that this may be an optimal solution, but it cannot be the only optimal solution. And why is that important? It's important because once you establish that you can focus only on these corner points, then you don't have to examine infinitely many possibilities. So if you can establish that there is always an optimal solution that's like this, okay, which is a corner point, then because there are finitely many corner points, and we're going to see why, we reduce the problem of linear programming to examining finitely many possibilities. Okay. So far we don't even know whether that is possible, right? We have a problem, we draw the feasible region, there are uncountably many feasible points, and to find the best solution, potentially you may have to examine and infinitely many of them. But this observation says that that is not the case, that you can get away with looking at some finite subset of those points. Okay? So even though the picture tells us, it gives us some valuable information, now we have to sort of ask ourselves, what does a corner point mean when we can't draw a picture? Is the question clear? So once again, there is something special about points that look like this, and what is special is that if you identify all of those points, then you can solve the linear programming problem by just plugging in those points into the objective function and picking the point that achieves the largest value. Okay. So how many of you are convinced by this observation? Okay, don't be shy. Okay, how many is anyone not convinced? Okay, I mean, I do see, yes.
It's concave shape, then the corner point is not the best.
If what is concave shaped?
The region we cover in the graph, the coordinate is the concave shape.
You mean the feasible region?
The feasible region.
Okay. So you have to tell me what concave is. Okay, so for that feasible region, so here's another feasible region. Okay. Okay, so let's say that this is the feasible region. Okay. So then, would something like that be true? Is this what you're saying? Okay. But actually, this won't be the feasible region. Okay. So let's see why this cannot be the feasible region of a linear programming problem. So for this to be the feasible region, you must have a line that looks like this. Okay. Agreed? Therefore, this cannot be in there. Okay, so we are getting into territory that's really not necessary at this point. Okay, so first of all, you cannot have shapes like this as feasible regions. Okay? So what you have is, so your feasible region is what's called convex. Okay? So what does this mean? It means that for any two feasible points, the line segment between them is feasible. Okay. So you take any 2 points in your feasible region and you join them by a line. The line segment lies within your feasible set. Okay. So here, for instance, if I take this and look at the line joining them, that line leaves the feasible set. Okay. Such a region can never arise as a feasible region of a linear programming problem. We'll see why a little bit later. But geometrically, this should be clear to you. The way we get this feasible region is by looking at half spaces, which are one side of a hyperplane, and we are looking at an intersection of half spaces. Okay? So we have a line, one half of which is feasible, one side of which is feasible, the other side is not. And you look at intersection of a whole bunch of lines. The feasible region has to have this property in that case. Okay? Yes.
What if you make both in that previous shape order there?
Mm-hmm.
What if you make both the vertical lines headed to the right, and then the top horizontal line heading down, and then the bottom horizontal line heading up?
Do you want to come and draw that for me here? Okay.
Or whatever. Get that thing.
Mm-hmm.
Both this way. Down.
Okay. So let's again examine this, and after this we'll abandon this little shape. So if you have this line and this line, okay, remember that your points have to satisfy all the constraints. So the moment you have this, none of these guys is feasible. Okay. So this violates this constraint. Okay. Cannot be feasible. Okay. Is that clear? Because you only care about points that are on this side of this hyperplane. So anyway, hello? Oh, let me check. Well, the microphone's on, but do I have to change that? Yeah. Oh, okay. Okay. So buzz me again. Yeah. Okay. Right. Okay. So let's actually not worry about this for the moment. Okay. And again, examine the question or the issue that I mentioned. So any point that's in the interior cannot be the unique optimal solution, cannot be the only optimal solution. And that's because in a linear programming problem, where if we look at an iso-cost line, a line along which the objective function has the same cost, such a line can be moved in one direction, such that you still stay within the feasible region. So this is true for any interior point. Therefore, if this is optimal, then the points that you get by moving in one of those two directions will still have to be optimal. So, as I said, let me restate what this accomplishes. All it says is that if you have a linear programming problem, as long as you can enumerate all of these special points that are called corner points, you can always solve a linear program by plugging in, checking the objective values at each of these corner points. Okay? So that's what this result says. We are going to formally prove this a few lectures from now, but for now this is just an observation that happens to be true, and there's some sound reasoning behind it, at least in terms of a picture. Okay. Now, what is special about each of these points? So how did we obtain this point? Yes?
They're all solutions to linear functions, I guess.
Okay, so they're all intersections of two equations. They're all solutions to a system of two equations, right? So you get this by solving these two equations. We got this point by solving these two equations. Okay? What about this point? So you have these two inequalities that if you view as equations, you get this point. Very good. So what it suggests is that there's nothing different from this inequality and these inequalities. So they're all the same. Right? We have a system with 5 inequalities, and you pick any two and you solve, you get a point. And every corner point is obtained by solving some two of those inequalities, those equations. Now, so when you have 5 inequalities, how many pairs of two equations, how many sets of two equations can you get? 24. Why? Okay, I heard 10. So 10 is right. So it's the number of ways of choosing 2 out of 5, you get 10. How many corner points do we have? 5. So what happened to the others? Well, we just said corner points are obtained by solving some two equations. So I guess that doesn't rule out, some. Okay, so it doesn't rule out some pair of inequalities giving you a point somewhere here. But that's not a corner. So if your first observation was right, that every corner is obtained by solving two inequalities, and every two inequalities give you a corner, then
I guess these 5 are within the region of the other 5.
Okay, very good. So so these 5 are actually feasible. The others are infeasible, meaning that they don't satisfy the other inequalities that remain. Okay, so after all, we are taking 2 of these and solving them. We get a point. There's no guarantee that this point satisfies the remaining inequalities of the problem. So for instance, I could take this and I could take, so let me write this down this way. So I have x1 non-negative, x2 non-negative. So I could take this and this. When I solve them as equations, what do I get? I get this point. So that is a corner by our definition, it's just that it's an infeasible concept. Does not satisfy these other inequalities. So we don't care about it. And you can locate the others in much the same way. So it seems like to get a corner point, you solve as many inequalities, you set as equations as many inequalities as you have variables. So here we have two variables, and we pick two equations and solve them. Something, right? Yes.
I have a relevant question to ask. What if we change the direction of the inequality to the first equation? Minus x1 plus x2 is bigger or equal to 5. And what will happen?
Okay, so the question is, what would happen if we change this reverse the direction of this inequality? What do you think happens?
It means like the upper half space of like that line, and that means like it's kind of like open space and then never reach some kind of like optimal solution.
So the question once again is, what happens if this is reversed? And the answer is that one of two things could happen. So, for instance, in terms of the picture, we can see you may have a feasible region fits into exactly one of these categories. And if you relax the feature that we mentioned, then you don't have such a result. Yes.
And also like for those infeasible like in linear programming, and if in reality we go to like manufacturing plant and manager wants us to do something and we say, oh, it's infeasible, and then you have that tool.
So what do you do if your linear program is infeasible? So typically, infeasibility just says that your model formulation somehow has a gap, right? So maybe there's some mistake you made, or in effect, it just says that all your constraints taken together are incompatible. Maybe you're being too stringent. This is like saying you should finish this project day before yesterday, right? You're there now. It's unrealistic. So if in a real world problem you observe infeasibility, it typically means that you have to go back and examine your constraints and see whether what you really want is what you've written down. But yeah, if you formulated your problem correctly and it's infeasible, then it just means that you're asking for too much. Any other questions? Okay. So I want to now go back to the observation that we get corner points by taking any two equations, and any two inequalities, and solving them as equations. Okay, so let me get rid of these. Let's actually do the following. So I'm going to take that linear programming problem and rewrite it as equations. So now I have a system of linear equations. There are 5 variables, 3 equations, and all of them have to be non-negative. And of course, I want to maximize a certain objective function. Now, this is called the standard form representation of a linear program. Some books would call it canonical form. And if you're using different textbooks, or sometimes within the same textbook, people often mean different things by these different words, or maybe they mean different things even by the same word. There's a lot of inconsistency. So basically, what it means is the following: that every linear programming problem that we examine in this class will have a maximization objective. It will have non-negativity constraints for all the variables, and it will have equations. So this just means maximization objective, non-negativity for all variables, and only equations.
What do you mean by only equations?
So I just only equations, no inequalities. So any linear programming problem is said to be in standard form for our purposes, for this class, if its objective function is a maximization objective function, if all the variables are constrained to be non-negative, and every constraint is an equation. Now, in a general linear programming problem, your objective could be to maximize or minimize. Variables could be non-negative, non-positive, unrestricted. It could have, and you may have inequalities going one way or the other way in addition to equations. Okay. So it's actually not too difficult to see that any linear programming problem can be converted into a linear programming problem in standard form. So your textbook discusses it. It's actually fairly easy to do it, so let's actually quickly do that. If you have a minimization objective, what happens? If you want to minimize 4x1 minus 3x2, this is the same as maximizing minus of that quantity. Okay. So if you're given a minimization problem and you want to convert it to a canonical form, you just negate the objective and write it down as a maximization problem. How many of you agree with that? Okay. So is there any question about that? Nothing, right? Okay. How about, so this is the objective, okay? Now let's deal with constraints. If you have a constraint like 3x1 plus 2x2 is at most 7, how do you convert it into standard form? Just add a new variable, 3x1 plus 2x2 plus some s equals 7. And notice that s has to be non-negative, so it's already part of the standard form thing. And if this were bigger, you would just say 3x1 plus 2x2 minus s equals 7. So for less than equal to constraints, you will add a slack variable, and for bigger than equal to constraints, you will subtract a surplus variable. So every constraint has to be an inequality like this, or an equation. If it's an equation, you don't disturb it. If it is an inequality or one of these sorts, you introduce a new variable. and convert it. Now what about, so these are the constraints. And now the variable restrictions, right? You could have x1 if it is non-positive. So you have a linear programming problem where x1 has to be less than or equal to 0, then what do you do? No, but notice that x1, you want all variables to be non-negative.
And minus x1.
Right? So you use minus x1 instead. So what that means is set y1 equals minus x1, and wherever x1 appears, use minus y1. Replace all x1s by minus y1, and y1 of course will be non-negative. Okay. So now you've changed your variable from x to y, and you have non-negativity. So x1 is no longer a variable for your problem, y1 is, and y1 is non-negative. Yes?
I can't read the top line.
Yeah, okay. So let me read it out, and sorry for the small writing. So whenever you have a variable restricted to be non-positive, use its negation, meaning use a new variable which is non-negative. So I set y1 equals negative x1. So y1 would now be restricted to be non-negative, which is what we want. And wherever x1 appears, use minus y1.
Okay.
Finally, the only difficult case, if you can call it that, is when there is no restriction on the variable. So when x1 is what's called a free variable or unrestricted. So in this case, you replace x1 by y1 minus z1. So you're introducing two new variables. So two new variables. And y1 and z1 are now both going to be non-negative. And wherever x1 appears, you use y1 minus z1. So the reason is that any value can be represented as a difference of positive of positive numbers. And so given any value of x1, you can find non-negative y1 and z1 such that y1 minus z1 equals that x1. So for every unrestricted variable, you will use one extra variable because you're replacing one variable by two. But this converts it to standard form. And in your homework, you'll have a little exercise that just asks you to go through these rules. Yes?
I have a question about constraint part. Why does it change to equal?
That's because I'm going to let S represent the difference between 7 and whatever this quantity is.
So S doesn't have to be an integer.
S doesn't have to be an integer. It just has to be non-negative. So any questions about this? This is discussed in the first part of chapter 3 of your text. So, so once we move to coursework, which will be early next week, for every lecture there'll be reading from your textbook. The appropriate sections will be listed so that you can follow along. Okay. Okay, so now what I want to do is start with this system of this canonical form linear program. Okay? and make a few observations about it and outline the simplex method. So that's what we'll do in the next 15 minutes or so. So if there are any questions, please ask me now. Otherwise, we'll continue with this. Okay. So, I still want to keep the pictures, so that means I'm going to have to erase what I wrote down most recently. Okay. So, because we are always going to work with canonical form problems, unless otherwise mentioned, we'll take all variables to be non-negative. So I don't have to tell you this. And we'll take the objective function to be maximization, so I don't have to tell you this. So when you see something like this, you should already know that we're looking for values for x1 through x5, satisfying all of these equations and maximizing this. Okay, so I want to write this set of equations. I want to rewrite it in a way that makes it a little more transparent. So let me say that this is x3 equals 5 plus x1 minus x2. 4, 35 minus x1 minus 3x2. And x5 is 20 minus x1. So I've taken each of these equations and I've just written them in a slightly different way. And this presentation is meant to convey the following idea. That we can think of x1 and x2 as values that are under our control. And once you figure out values for x1 and x2, the values of x3, x4, and x5 get determined by the set of equations. This is just a point of view. So really, when you go back, you see that there are 5 variables and you have 3 equations. So you have 2 degrees of freedom. So you have 2 variables whose values you can fix to anything you like. Once you fix the values of those 2 variables, you have 3 equations and 3 unknowns that you can hope to solve. And typically, when you solve 3 equations and 3 unknowns, you have a unique solution. Not always, but typically. So I just want to make that visually transparent by saying that I'm going to pick values for x1 and x2. I'm going to set them any way I like. And that will in turn determine the values of these 3 variables. Okay? Okay. So you can set these values to anything you like, but it seems like a natural place to start is 0. Okay? So if you set these values to 0, what you observe is that you can read off the solution just by looking at these numbers, because this entire stuff is 0, so I don't have to worry about this mess. And that solution corresponds to this particular point in the picture. So this is the point where x1 is 0, x2 is 0, and x3, x4, x5 assume values 5, 35, and 20 respectively. And of course, I just want to keep track of my objective function. So let me say that my objective function depends on x1 and x2 in the following way. It's actually 0 plus 2x1 plus 3x2. And therefore, when I set x1, x2 to 0, I have 0 as my objective value. Now, of course, you're not constrained to set x1 and x2 to 0, right? You can choose values for them, and these values can be anything you like. Therefore, maybe it makes sense for us to think about increasing the values of x1 and x2 because we get more money. We can increase our objective values. So we are going to try to increase the values for x1 and x2. So the goal is, of course, the question that you started out with is what values of x1 and x2 should you use to achieve maximum profit? This is nothing more than restating the same question. Okay? So what values of x1 and x2 should I use so that they satisfy these equations? Of course, if I set x1 to be 20 and x2 to be 5, then I would get values for x3, x4, x5, and a value for z that is an optimal solution. But let's pretend that we don't know, and that we are here, and we want to think about increasing x1 or x2. So suddenly it seems like having x1 positive or x2 positive is a good thing, because it's going to increase your value of 3. So why not keep increasing then? So you could say, so I'm going to try x1 equals 1, x2 equals 1. I want to fix values that way. But if you carry out that reasoning to its logical end, you really end up with the same question, which is, what should I set them to be? Should I increase them simultaneously at the same rate? Should I increase them such that, for every increase in x1 I get $2, and for every increase in x2 I get 3. So maybe I should increase x1, 1.5 times faster than increasing x2 so that I get the same profit out of them. But these all seem ad hoc, right? And after all, any strategy for increasing has to somehow pay attention to the constraints as well. Clearly, if you look at the picture, we can increase x1 all the way up to 20. That is, of course, assuming that x2 is fixed at 0. If instead you fix x1 at 0 and increase x2 all the way, you can go all the way up to 5. And if you increase it simultaneously, maybe you'll go in some direction inside. So to not worry about all of these possibilities, okay, so here we have 2, so we just have to examine increasing one or the other or both. If you have a few thousand variables, then it becomes much more complicated. What particular combination of variables do you choose to increase, and precisely how? So to take all of the guesswork away, we could sort of do the following: that we're going to fix one of the variables to be 0. Okay. Or let me say that differently. You're going to fix all of the other variables at 0 except for 1, whose value you're going to increase. So when you have 10 different variables here, 9 of them will be held at the same level that they are right now, which is at 0. And only one of them will have its value increased. Okay? And subject to this restriction, we want to know where we end up. Okay? So for instance, suppose we say that we want to increase the value of x1. Let's actually make it a little more like this. So we want to increase the value of x2. So this is going to be fixed at 0. And we are thinking about increasing x2. Now, this coefficient says that for every unit increase in x2, you are going to get $3. Right? So how high would you like x2 to be? 1? Why? So you increase x2 by 1, you get $3. You increase it by 1 million, you get $3 million. What would you like better? So the right answer is as long as I can increase it, right? Yes.
Yes, I understand like increase like x2, you get like more value than increasing like 1 unit of x1. But you know, like I'm just wondering, like, does that matter? You choose to increase x1 first?
It doesn't matter.
Doesn't matter.
It doesn't matter. Well, it matters and it doesn't matter, and we'll know in a little while. But for now, it doesn't matter. You want me to actually increase x1? We can do that too. I don't have it worked out, so I'm going to do this just like you're going to do this. Okay. So let's think about increasing x2. Okay.
You can use those equations to get like x2 replaced by some x1 and x2, x4.
That's what we're going to do. So I'm going to do one equation of that before we finish today. So suppose we decided that we hold x1 fixed, we want to increase x2, and for every unit increase we get $3. So of course we'd like to increase it as much as possible. But what might happen? Suppose I set x2 to be 100. What happens? Notice that as I change x2, the values for x3, x4, and x5 change. And they change in a way given by these equations. So our strategy of not worrying about, not modifying any variable that's on this side except for 1 makes it easy to evaluate the effect of such a change. You don't have to worry about x1. And again, you should think about having thousands of variables on this board on the right-hand side. You don't have to worry about any of them except for the one involving x2. So as you increase x2, this value of x3 is going to go down, right? So this is going down. And we know that all our variables have to be non-negative. So this says that x2 can increase up to 5, but not more. If you increase x2 beyond 5, you run into trouble. Okay? What about this? Again, x4 also goes down, but this says x2 can go up to 35 over 3. The exact value doesn't matter. What matters is the fact that this is actually bigger than this. So we are going to hit this constraint before we hit this constraint. Now what about here? This has no effect. Okay. So if we decide to increase x2, we can increase it up to 5. So any increase up to 5 is okay, but anything beyond 5 is not. So now we change the question to, for every unit increase in x2, you get $3, and you're allowed to increase it by up to 5. What will you do?
X2 to 5 and try to maximize x1.
You will, okay, so first you will set x2 to 5. Okay, so that's the answer that we need at this point. Okay. So we are going to now set x2 to 5, and now what happens? x3 becomes 0, x4 becomes 20, and x5 becomes, x5 just stays at 20. It doesn't care what x2's value is. So you end up with this solution. Is this clear to everyone? Now in terms of the picture, what have we done? we started here and we moved up to this point. Now notice that if you start at a corner and you go in a certain direction, you're going to go all the way in that direction until you exit the region. Because going any further would cause you to leave the feasible region. That's why you stop there. So if you stop, that means some other variable has dropped to 0, okay, because that's what it means to leave the feasible region. Okay, so we want to now capture this increase by a set of equations that serve the same role that this set of equations did for the origin. Now, what does that mean? It means that we want to rewrite these equations in terms of such that the right-hand side has x1 and x3, because we want the right-hand side to have those variables whose values we determine, and we determine them to be 0 always. So you want to rewrite this system so that x2, x4, and x5 are expressed in terms of x1 and x3. Okay? Is that clear to everyone? And so let me quickly do this rewriting before we start. It'll only take a couple of minutes. So I want to rewrite everything in terms of x1 and x3. So first I examine this. And this is the equation that limited me from increasing the value of x2. So you start with that equation and rewrite it in a convenient way for you. And the convenient way here is just say x2 is 5 plus x1 minus x3. So now I have x2 in terms of x1 and x3. I want x4 and x5 in terms of x1 and x3 also. Okay, but I've already done the hard part. x4 is in terms of x1 and x2, but I know x2 in terms of x1 and x3, so I could just substitute it here. So this would be 35 minus x1 minus 3 times 5 plus x1 minus x3. If I simplify this, I'm going to get everything in terms of x1 and x3. And this already is in that form. So let me write down what we get. If x2 is 5 plus x1 minus x3, x4 is 35 minus 15, so you get 20. There's minus x1 minus 3x1, so there's minus 4x1, and plus 3x3. X5 is just 20 minus x1. And I want the same thing for the last row also. So I'm going to let z equals 0 plus 2x1 plus 3 times 5 plus x1 minus x3. So I get z equals 15. That's from here. Okay. The x1 coefficient is going to be 2 plus 3. And the x3 coefficient is going to be 5. So, let me quickly explain what we've done. We've rewritten our set of equations. All we did was just rewrite terms, move certain terms to the right and substitute certain equations in certain others and so on. So the solutions are preserved when we go from one system to the next. Now the advantage of this system is that this corresponds exactly to the solution that you move to. Meaning, if you started with x1 and x3 as your set of variables whose values you hold to 0, and express the other variables in terms of these two, this is what you would end up with. You can read out the current solution just by looking at this system. x2 is 5, x4 is 20, x5 is 20, and z is 15. And not only that, this solution from here, this last row tells you the following, that for every unit increase in x1, you're now going to get $5. It was 2 before, but now it's going to be 5. And for every unit increase in x3, you're going to lose $3. So from here, you have no choice. If you want to increase something, you would increase x1. And if you want to increase x1, then you want to look at which equations limit you from increasing x1 beyond a certain amount, and so on. Okay. So what we just did was one iteration of the simplex method. And if you do this repeatedly, you will end up at an optimal solution. So we'll pick things up next time, but I'll be happy to answer quickly any questions you may have.
So I got lost. Why you chose again x1 and x3 can't down?
That's because x1 I already held to 0, and x3 was responsible for my not being able to increase x2. Okay? So x3 was positive before, and it dropped down to 0. Yes?
So you would continue doing this rewriting until you got to a point where increasing any variable was decreased.
Exactly. Yeah.
For the 2x1 x1 equation, does the 5, 20, and 20 and 15 have any significance?
5, 20, 20, and 15. That's the current solution. Right? x2 is 5, x4 is 20, x5 is 20, x1 and x3 are 0. The current objective value is 15. So it just captures the state of your computation at this point. Yes.
What is this called, this method?
Simplex method.